Okay. Is it, oh, that didn't stick on my ear. All right, is that good? Ah, wow. It's like I have an echo. Okay. So PyEphem, so you get an observer. You need to know where on Earth you are and when you are. And Ephem already knows about big cities like Columbus. So apparently we're big enough. And it'll default to right now. So if you just want to say, hey, give me Columbus, it'll tell you about right now. And then you have bodies, and those are whatever's up in the sky. It can do asteroids, stuff in our solar system, a bunch of stars. And then you need to do compute steps, which is you take the body and you tell it where the observer is and you figure out how they're related. So that's the basic idea of what you do with PyEphem. And to know where you are on Earth, you kind of have to know what the coordinate system is. So you've got the horizon. So I'm standing on Earth. This is Earth because it's green. And that's the sky and it's blue. So you're standing on Earth. And so you've got north, south, east, and west. You've got a horizon line. And you call the horizon line the azimuth. And so the azimuth is 360 degrees. North is 0, and positive is to the east. And then altitude is how high you are above the horizon, or how high it is. And straight up overhead is 90 degrees. And there's a really cool trick on how to figure out how many degrees up something is your fist at arm's length is 10 degrees. So if you want to know, okay, there's something about there. So it's 10, 20, 30. Turns out that the top of the trees tend to be at about 30 degrees. So when you're trying to figure out how to make sense of the coordinate systems you get from PyEphem, you need to understand a little bit about altitude and azimuth. And of course, you have to worry about time because things are moving really fast. And another hint, when you're looking at, north, south, east, and west, you turn your head up, and it's kind of a mirror image. So if you look at the compass rose on the sky, it'll be a little backwards looking. And that's because when you look up, things flipped a little bit. And so here's an example of using ephem to figure out the sun moving across the sky, just a representative body. So our location, we tell it ephem.city, and we put in the string Columbus, and we have our observer for right now. And then you create a sun object. So ephem has a bunch of built-in objects for solar system bodies, so we've got the sun. And you give it your location as your input parameter, and the compute happens as you create the object. So everything in that other slide, all 3 steps, they just happened. And then you want to ask, okay, so where's the sun right now? So in the compute step, it figured out the sun's altitude and azimuth, the 2 coordinates we listed on the last page. And it'll tell you the other things it calculates is the transit time. So solar noon is the highest the sun's going to get in the sky, because it kind of does that thing. And you can figure out when it's going to be at its highest point. That's a really cool thing to know. And it doesn't compute rise times and set times, but they're really easy to find. They're other functions. So you say, well, when's the sun going to rise next? And when's the sun going to set next? So pretty simple. Another thing you might want to do with the sky is figure out when twilight's going to happen. Now, there are 3 different twilights. Is anybody familiar with this? Okay, so the sun sets, and it's not totally dark yet. Because the sun's just below the horizon, there's still a lot of light coming in. So that's civil twilight. Civil twilight means you can ride your bike home and you're not going to crash, even if you don't have good lights, pretty much. And then the sun keeps going, it gets darker. Now you're in nautical twilight, which means if you're in a boat, you can start to navigate by the stars. And then things get darker, and then you hit astronomical twilight, where you can suddenly get dark enough to start getting some astronomical data that's actually useful. And then you hit full dark. So what you're asking is, how far below the horizon is the sun? So you think, okay, I should go to PyEphem and ask it, okay, when is the sun this far below the horizon? Except that's not actually the way you ask that question. You tell it, the horizon is below the horizon. Now when does sunset? So you can move the horizon around. It's really cool. Other uses for moving the horizon is, say, you don't care about anything over the trees and you wanted to know when is this planet going to come up over the trees, you set your horizon to the top of the trees. So resetting horizons are really useful. Or if you're on top of a mountain, the horizon will be lower than straight across. So this is the US Naval Observatory. So they do tons of cool stuff like, sunrise and sunset. And the way they calculate it, this is all in PyEphem's documentation. There's all these cool corrections for the atmosphere because things warp down by the horizon and things get weird. It's like, okay, we're not going to worry about that. Turn all that off. So you turn off the pressure just to be consistent. And then, so let's say we want to know when astronomical twilight happens. So that's when the sun is 18 degrees below the horizon. So you just take Columbus and you move the horizon down by 18 degrees. So the default when you're calculating sunset is when the edge goes dips below the horizon, but twilights are calculated by the center. And there's a handy little use center argument for that. So you just say when is the sun going to rise with the center when the horizon's down at 18. And that will be the time when you should probably stop using your telescope because your data is going to be noisy junk because the sun's coming up. So then one of the pieces of my code up on GitHub is I took a bunch of the stuff the sun does and decided to put a little text output to tell me all sorts of things. So you can see I made a special location just for PyOhio at 11 a.m. So any of my code that supports fancy location stuff, which I'll talk about later, I tried to put the examples in from right now. So right now the sun is at 50 degrees and it's at 109, which is to the east. So altitude 50 degrees, so 1, 2, 3, 4, 5, between 0 and 90, sun's about somewhere up there. And the sun is to the east. It's probably either going to be to the east or to the west because it's the sun. And so sunset tonight will happen at 20 o'clock, and all of these are in 24-hour time. Bedtime will be at 22 o'clock if I want 8 hours of sleep. And I have it set up so I can change how many hours of sleep. So maybe I only need 7 hours of sleep. I can put that in there. If I'm really tired, I can tell it 10, and it'll tell me when I should go to bed. And I know when sun will rise tomorrow morning. The sun is going to rise at 6:30. I am not getting up with sunrise during the summer. And we will have solar noon at 1:30. So solar noon is nowhere near noon. We're in daylight savings time, but even if we weren't, the sun is still at transit half an hour off of noon. So, our clocks aren't really that synchronized to the sun. And all that stuff about the U.S. Naval Observatory's calculations for twilights, here they all are next time they're going to happen. So then you can just see all of that. And it's good for, if you're planning on doing something that day, where's the sun going to be, whatever, you can ask it real quick. Another thing PyEphem can do is the seasons. Now, I just told you that everything depends on the observer. The seasons don't. So all you need is a time, and you say, okay, so when's the next vernal equinox, autumn equinox, summer solstice, winter solstice, solstice. So the summer and winter, autumn, those are obviously based on the northern hemisphere. So if you're in the southern hemisphere, when it says autumn, it means spring, and all that's backwards. But all you need is a time, and it'll tell you when the next equinoxes are. So if you want to know when spring is going to happen. Another important thing about stuff in the sky is they have phases. So our sun shines, light bounces off of stuff, and we see the light that's bouncing off. You're most familiar with this for the moon, but all the planets have phases too. So say if there's a planet on the, So if there's a planet sort of to the side of us, and the sun's illuminating that part of it, we could have only a half phase on one of the planets. So that'll tell you how much of the planet you'll be able to see. So, all right, we're in Columbus. Tell me about the moon. What's the moon's phase? It'll give you a floating point number. It's a percentage from 0 to 100. And you can ask it, okay, what phase is Jupiter in? And much to my amusement, you can even say, what is the phase of the sun? That's always 100%. The sun is always shining. Yeah. What? Yeah.
I was asking about moon phases.
Right.
If you have two values for 100%, I guess it could be on either side of the full moon, right?
It doesn't. It's percent illuminated. It doesn't tell you which direction. No. So same way I had the solar code, I wrote a little piece of lunar code. So if I want to know what the moon's doing right now, I say, what's the moon doing right now? This one's just in Columbus. I didn't get this one for PyOhio. But so I think this is from a few days ago. So the phase was just 6% illuminated. The moon's going to be a pretty small sliver. And so it'll tell you when it'll set, when it'll rise, when it'll transit. And you notice that it's in a different constellation each time. The moon moves really, really fast. The moon never rises. And if you see that the moon rise like one night around sunset, and you're like, that's really great. I'm going to come back here tomorrow with my camera. It's not going to be there tomorrow. The moon moves really, really fast. So that's important to know. And then we do have, there are functions for first quarter, full moon, last quarter, and new moon, and that's how you'd figure out what phase it's in. Same way there's like next sunset, next sunrise, you can ask when the next quarters are for the moon. And by the way, those are also independent of location because the moon is always going to be illuminated a certain percent from the point of view of the Earth, no matter where you are on the Earth. Southwest, north, north-east, those are the directions, and those are the, I don't think those are the constellations. I think those are the, what's the word for it? Anyways, they're later in my talk.
Oh, sorry.
Yeah, yeah. But I will talk about that later. Exactly. And so, something about constellations. Now, what we call constellations are actually asterisms. So when you look at Orion, Orion is an asterism. It's a bunch of stars that make a picture. So at some point, the astronomer says, okay, we're going to group this sky into a bunch of constellations. We're going to pick a bunch of asterisms that don't overlap. We're going to draw arbitrary lines between them and call that a constellation. So you have, these are very standardized things, and the lines are really funky now. When they first drew them, they were a bunch of nice straight lines, and then things moved. So the constellation boundaries are a little funky. But you can ask about any of the bodies. You can ask what constellation they're in right now. You can't see that very well. So you just ask it. Ephem has a function called constellation. And you see here we've got a moon object. We have computed it for our location. And then you just run the constellation function on your object, and it'll tell you what constellation it's in right now. So that's really cool. Like, if you found a planet, you can say, what constellation is that in? And that can help you find your way around the sky. Okay, in case anyone has been following along at home, you probably got a whole bunch of nonsense answers, like solar noon happening at 5:30. You're pretty sure that's not right. That's because I haven't put a little bit of extra code in there. I wanted it to look really clean, but PyEphem does store everything internally in UTC, so you're going to want to convert to local time to make any sense of the numbers you're getting out. So you can see sun.transit time on the 17th, yeah, it says 17 o'clock. No. So then you put it in local time, and you'll get a Python datetime function, Python datetime object back from the standard library. And ISO format is a really cool function if you want something that's just a little easier to read. It'll tell you, year, month, day, hours, minutes, seconds. So just be warned. So now I'm going to go through a section on what's that thing. All right, so you ever walk outside, you're like, oh, look at the stars. Wait, that one's really, really bright. I think it's a planet. Maybe it's a planet. I don't know. I don't know what the planets look like. I don't know where they are. So you go in and ask Python, okay, where are the planets right now? And so right now, at 11 a.m. today, Mercury is at 64 degrees above the horizon towards the southeast. Its phase is 30%, so it might be hard to see, but it's high up enough to see. Venus might be behind the trees. Mars, yeah, we're probably going to see Mars. It's up at 70 degrees and its phase is 98%. So we probably can see Mars. Jupiter ought to be pretty visible. Saturn is below the horizon. We're not going to see it. Uranus is behind the trees, and Neptune is below the horizon. So if you see a star out there, you can go out and say, well, where are all the planets right now? I'll talk about that later. That's later. Okay, so let's say you went out and you took a picture at night and there were stars and you're like, that's cool. I bet there's a constellation in there. How do I find that out? So the first thing you do is, hopefully it's a digital camera, so you have metadata so you know exactly when you took it, because you need to make an observer, and the observer needs to know what time things were. And so then you figure out your terrestrial coordinates, so you have to know what way you were looking. That kind of matters. But if you happen to remember what way you were looking when you took the picture, it's really easy to figure out. And so then you can find what constellation that matches with, Or you can take the celestial coordinates and go look up a star map. And then, so I'll show you how to read star maps, which honestly I only figured out because I was working on this talk and thought, hey, I should put a star map in there. I don't know how they work. Okay, so if you're going to figure out where things are in the sky, we've got celestial coordinates, which are different than our terrestrial coordinates. And a great circle is a fun word I found on Wikipedia, which means if you have a sphere and you draw a plane that goes through the center, the circle that will make on the outside edge is called a great circle. And so there are two really convenient great circles for the Earth. One of them is the, what's that one called? The ecliptic. The ecliptic is in the plane of the solar system. Like if you have the solar system and it's flat and you've got the sun, you've got all the planets, and you draw a line straight through the middle, that's our ecliptic. But the Earth is rotating at an angle, so we also have the equatorial system. And it is common, and astronomers today tend to use the equatorial system. So the Earth is spinning. So in the same way we had altitude and azimuth on the Earth, we have latitude and longitude in the ecliptic system and RA and Dec in the equatorial system. Yeah, you can tell I'm not an astronomer. I keep reading my notes. And the really convenient thing about this system is we have these things called the solar poles. Or not solar. Anyways, the poles. So we have at Dec 90 degrees, we have the northern pole, and at Dec minus 90 degrees, we have the south pole. And so the Earth is spinning. And so the poles are actually really, really cool. So the southern celestial pole down in Chile, I left my camera out there for 30 minutes, and this is what the stars do over 30 minutes. That's how fast they move around the poles. And you can see a car drove by. That's headlights at the bottom. So, now that we know how the celestial coordinate system works, let's take this picture I took. This was somewhere north of Columbus, a little north of Powell. Columbus is pretty close. So I import ephem, and I make Columbus. No, it's not, actually. So, and then I put the date in there, but remember that PyEphem is using UTC, so I subtracted 5 hours. This was in winter, there's no daylight savings time, so we were actually UTC minus 5. There are probably fancier ways to make Python do that math for you, but whatever. So then you say, there's this cool function, you take your observer, you tell it RA Dec of, and then you give it your altitude and azimuth. So 300 means, so north is 0, and I was almost west. So I'm most of the way around the circle, but I'm sort of between west and north. So north would be 360 degrees when you're going around that way. West is 270, so I was pointing 300-ish. And then I said trees happen to be sort of 30-ish, so I put 30 in there. You know, it's close. And so then I have the RA and Dec of that. And the RA Dec is these celestial coordinates, and the stars, over a good period of time, they don't move as fast as other things, so RA and Dec are pretty useful. And so I asked ephem, what's the constellation? And earlier, I was handing it an object that I'd run compute on, but all you have to do is hand it these two coordinates. So I take this function that I just wrote, feed it to the constellation function, and say, okay, what constellation is that? And right here, running off the bottom of the slide, its abbreviation is CYG. The full name is Cygnus, and Cygnus is a swan. So I went to Wikipedia and said, okay, what's Cygnus? So this is a star map. And up is the North Pole. So you can see all these lines are converging towards the North Pole. So this is the declination, and that's RA across the top. I think I got that right. And I also happened to look at that and say, hey, look, see that big star? It has a name. And you know how PyEphem knows a bunch of cities? It knows a couple stars, too. And if it's big enough to have a name on Wikipedia, PyEphem might know about it. So like, hey, let's check that out. And so I put the name of the star into PyEphem, and ta-da, it knew Deneb. So like, all right, now I'm in Columbus right now. This is the same Columbus I used on the last slide with the times and everything. And so it gives me the exact coordinates where Deneb was in the sky at that point. So 300, I was pretty close. Deneb is at 303, and at 34 degrees north. And I'd said, trees are at about 30. Well, yeah, somewhere around there. I was pretty close. And then I wanted to know, okay, so if up on that picture is pointing towards the pole, where is the pole related to my picture? So I decided, okay, let's make the pole. And a fixed body means things like the stars that aren't moving really fast. The moon isn't fixed because it goes all over the place. Stars are, over short enough time periods, pretty much not moving. So you can use the fixed body object. And then, so you put in its RA and dec, because you're setting this up, and the RA degrees on a circle that small, it really doesn't matter where around the circle you are. It's totally irrelevant, but I put in 0. And the North Pole is at 90 degrees, so I put that in there. I computed it for Columbus, and it told me in the sky that would be, well, that this is where it is in the sky. So, so you notice at close to 0, north is supposed to be 0. Yeah, that's pretty close. So 300 to 0 when 360 is around a circle, and 34 degrees up. So notice that this number is bigger than that number, so the pole is up in my picture. That's really all I wanted to know. So you can see where that arrow is pointing to the North Pole, and that arrow is pointing to the North Pole, so you want to rotate the picture I got off Wikipedia to figure out what's going on in the constellation, which gives me this. So this is Cygnus the Swan. Cygnus has its wings spread out, and it's flying headfirst into the trees. So now you know what's in your picture. And while we're talking about the North Star, there's actually a whole discussion of this on PyEphem's documentation. But it might be interesting to know, well, there's the North Star that we're using for north, but things keep moving a little bit. Is it really that close to north? So you can ask it. And right now, so we've got Columbus. And for now, the North Star is Polaris. So, you run your compute on it, you ask it the altitude and azimuth, and you see it's not even 1 degree off of north. So out of 360 degrees, and then 60 minutes, so it's like half a degree away from pure north. That's pretty good for the North Star, right? And then you can ask the RA and dec, whatever, in case you're curious, like, hey, does Polaris work as well in Moscow as it does for Columbus? Because Moscow's kind of far away, right? And they're in the north. So since it knows a bunch of cities, hey, it knows Moscow. And you can see that Polaris is even closer to north in Moscow than it is in Columbus, because it's closer to 0. So, hey, they have a better North Star than us. And then stars don't move very fast, but they do move. And around 3000 BC, Polaris wasn't actually our North Star. There was another star that was closer to north that people would use to navigate by, and PyEphem's documentation can go into details on that, but you want to know how bad it would be if you suddenly had a time machine and were in minus 3000 BC and were trying to find north? Well, Polaris would have been at 334 degrees. 270 is west. 360 is north. That's kind of bad. So they used a different North Star back then. All right. And so I keep telling you that things are moving. So of course, what do you want to do? You want to plot things that are moving, because they're based on time. So the first thing you have to do when you're going to make a plot, time versus location or whatever, is you need a list of all your timestamps that you're going to run your data for. And there are 2 different, both completely valid, easy to use ways to figure out your time sequence in the first place. You can either use Python's datetime module, or you can use PyEphem's time functions. So I've got examples of both. So if you're going to use datetime, the very, very, very basic outline of how you'd make a plot, you import datetime. I've got a number of days. So I've got a start date, and I'm making that UTC timestamps for now, and I'm using UTC so that there's none of that confusion converting for PyEphem. And then I pick an end date, and I make a list for my timestamps. And then I just say, well, the current date, when I'm not to the end date, notice I'm using datetime.timeDelta, and it's every 15 minutes. So I'm making a list of timestamps every 15 minutes between my start date and my end date and dumping them in a list. So here we have all my X values for my plot. So now I need some Y values, because if I'm going to plot something, I need something to plot. So I'm also making local timestamps because I don't want to deal with the ones in UTC because my plot will be weird. And then the Y values, and then you just loop over all your timestamps, and you set your location's date, location.date, that's your PyEphem location. You just set the date to your datetime object, it works just fine. And then you do whatever your calculations are, you append them to the Y value list, and you also append your local times. So, oh yeah, time conversion, that's ephem.localtime. I put something fancy in there that I've never used so that I could have different time conversions if I was in a different time zone, but I haven't actually used that yet. So, so that's the way I would make it with datetime. And if I'm using just the PyEphem module, so, you know, you do pyephem.now, that's easy. And then you make your start date, and PyEphem, you can import dates, you can input dates as strings, and it's year, month, day, hours, minutes, seconds, very standardized time format. And so you make, I was doing this, this is a plot over a year, and I was plotting each day. So I have a list of days that I'm going to plot over the x-axis, and then my y values. And so I have my start date, and so I'm saying, okay, while we're still in the same year, because this is a plot over a year, I'm going to set my location's date to the date I'm using right now. And then I will take my x values, and I will do ephem.localtime on the date, so I can get all my timestamps in something that makes sense to me. And then whatever my PyEphem calculations are, I'll do them there, add them to the y value list. And then for the next loop, using datetime, you do datetime.timedelta. In ephem, you have date plus 1. All the days are 1. So if you want another day, you just add 1. If you're doing different intervals, there is also ephem.minute, ephem.second. So it does all the math for you. You just use the names. You'll be fine. And yeah. And so then we have our x values, we have our y values, and we want to make a plot. So I'm using matplotlib and pylab. So first you make a canvas, and you can set custom widths and heights. So if you're making a really long, skinny plot, it's not stuck in the middle of a square looking really weird. And I'm adding a subplot. If you're just making one plot, it's just 1, 1, 1. If you're doing like rows and columns, you can do fancy stuff. It's just 1, 1, 1 most of the time. And then you make your axes, and you tell it your x values and your y values. You can change the colors. You can put the titles on, and you can put names and stuff. You can also plot 2 sets of data on one plot. I made a same time axis, but a totally different y scale, and put its data on there, put some labels on it, and you can either, oh, that's going off the screen again. Okay. And you can either print to the screen or you can print to a file. So you can save all your plots that you make too. So all that stuff I told you before about the sun over the year, I decided I was going to plot that. And so here you can see what the sun does in Columbus. So right now, it is not quite September 22nd. We are not to the autumn equinox yet. So I have yellow is daylight, blue is nighttime. So here are our sunrise and sunset, solar noon, are 3 different twilights. And you can see what happens at daylight savings time. You can see how, how early the sun rises in summer. The highest the sun gets at any point, the highest point it's going to get at solar noon. So right now, the sun comes up, the sun goes up, it's up. In winter, it gets less than 30 degrees in the sky. So if you want to know why winter's depressing, that's why. And then there's yes, this is Columbus. Yeah. And right, closer to the equator, it's a little more balanced. Closer to the poles, it's even worse. But for Columbus, yeah, the sun doesn't get more than 30 degrees high in the sky in winter. And then there's cloud cover to make it even worse. And so now I know why I'm always unhappy in winter. And you can also see like how many hours of daylight we've got if you take some of the difference. So that was just, and if you look in my code, you can see that I have the same x-axis values on all of them, so they all line up, but I named all of them differently. So I've got all the months labeled. I have the equinoxes and solstices, and then I've got the dates of the equinoxes and solstices, and I put them all on different ones so I can compare and see where I am in the year. Another fun thing you can do is the same data may look very different over 2 different timescales. So this is what the moon does. And the yellow stripes are when the sun is up, between sunrise and sunset. So that way you know if the moon's going to be up at night or during the day. And so this is the height of the moon in the sky, the altitude, and the blue line is the moon's phase. So you can see over the next 10 days, 124, okay, this is an old plot, but so around the time I made this plot, you see the moon was really close to full. The moon starts out, it's up during the day, it's up during the day, more during the day, and then it only rises like halfway through the day. So you can see between, like if it's sunset, if you wanted to go see where the moon was, look how much from one day to the next the moon's position changes right around sunset. The moon will not be in the same place from one day to another. And then if you start plotting it over longer time scales, you can see it makes these really cool sine waves. So you can see that the moon's phase does that, the moon's altitude does that. If you let it plot negative numbers, you'll see the moon's altitude is always pretty consistently going up and down like that. But I made it start at 0 because I can't see things below the horizon. And so I did the same thing for the planets. I thought, oh, this is great. I'll plot the phase of the planets too. And planets don't change as fast as the moon. So all the planets' phases are those straight lines at the top that are really, really boring. And you can see, let's see, which one's the moon? Okay, the moon is the blue one. See the blue one changing drastically over the plot? And then the planets don't move that fast. They move faster than the stars, but they look about the same each day. Really exciting. But then at least you know if the planet's going to be up when you're going to go out to look for it tonight or something. Another fun thing you can do with PyEphem is the separation. So if you have 2 bodies up in the sky and you've computed them both at the same location, you can say, okay, how far apart are they right now? And so I was reading the internet one day and said, oh, there's going to be this cool thing. There's a conjunction tonight. There's Jupiter and the moon. I was like, that sounds cool. I should get a picture of that, right? So, except I had plans that night that were going on till about that time. So I was like, okay, so when do I actually need to be outside to really see this? Like, how much time can I get away with? So I thought, well, I'll just have PyEphem plot this for me. So, this is going off the bottom again. So, see, this is a distance plot that I made. Junction is actually the name of the location because I put the timestamp in specifically to show you what the plot I was looking at was. So down at the bottom, I have timestamps by the hours. And you can see they get closer and closer and closer together, and then they start getting farther apart. So somewhere down here is when I want to be outside. And the blue line is the altitude of the moon, because I'm not going to make a big effort to go outside to see this really cool thing if it's behind the trees. But as you can tell, it's in radians. But anyways, it was up plenty high to see. So I looked at that and like, okay, it's good. I know what I need to do. And then, so I managed to be out there for this. That's the moon, there's Jupiter, and the Pleiades just went off the screen. So that was a time lapse. So I knew when I needed to be out there. I caught them moving apart. I got them in the frame of the picture. Okay. All right. So a couple of other things. As I was doing this, things got really annoying, and I decided, I've typed the same thing 20 million times, and I'm changing things that are hard-coded in my code. I should stop doing that. So we're going to use a bunch of Python standard libraries now. Argparse is really, really awesome. If you are making any command line utilities that you ever want options for, use argparse. So you make an argument parser, you give it a description, you can add arguments like -L location. So every time I wanted to make a plot that was from PyOhio, instead of just generically from Columbus, I just said -L PyOhio 13, and it made the magic plot for me. And -B body, like the one I made with all the planets, I have it set up so I can specify different planets, the moon, whatever, on the command line. -D, number of days, the moon plot, how I had it on 2 different timescales, I just gave it a different -D argument. -F for my plots, if I want output to a file, I give it a file name and it'll make me a plot. And then I started working on this talk. Oh, so I put a bunch of locations in a config file because I also got tired of, copying the same thing over. So I made a config file, and mostly that has locations. And I was all excited about this. And then I went to put my talk up on GitHub and realized that I was about to show everyone the exact GPS coordinates of my house and my friends' houses. So I thought, okay, those are going into a different file that will not be up on GitHub. So I found this cool thing called CSV. So you can import CSV, and my config file now has a list of other files to look at. It opens the CSV files and makes me a bunch of objects, of observer objects based on the information in the CSV file. And I even have an optional column for the date. And so I've got like one object in there. I've got Stonehenge and then historical Stonehenge. Like I was telling you, in 3000 BC, we had a different North Star. Well, Stonehenge used to line up with the sky a lot better than it does now because they built it a long time ago. So if you want to know about Stonehenge, you just make a location that's Stonehenge from a long time ago. Another cool thing you can use is ordered Dict. So you notice all the things I had in time order, like when's the next sunset, sunrise, when's bedtime. Well, if you make one of those in the middle of the night, they're going to be in a different order than if you make them in the middle of the day, based on whether sunsets happen for that day yet or not. And I wanted them to say, okay, what's the next one, and go in order. So what I'd start is I'd make a normal dictionary with all my items, and then I would turn it into an ordered dictionary and give it a sort on creation and sort it based by the timestamps. So I still have the exact same dictionary. I can iterate over it when I print it out. I didn't have to change the printout code whatsoever, but suddenly they were all in time order. And that's how I know. That's really cool because you can see whether bedtime is before or after sunset. Unicode data. This was asked about before. So Unicode has all sorts of really cool stuff in it. And they all have names that are all in all capital letters, and Python has a dictionary of every name for every Unicode code point. And it knows all the planets except Venus and Mars, because those are male sign and female sign. So I wrote a fun little thing that says, okay, so if I want a planet, I'm going to give it its name. I will turn it into uppercase. And if it's Mars or Venus, you change the name, because it doesn't actually know the planets. And then you just try and look it up using Unicode data. And so I don't have to know the Unicode code points. I don't have to look them up. All I do in my Python code is give it a string, and it will return the Unicode symbol for that string. So that was pretty fun. And then I wrote this really fancy piece of code. So labeling angles. There are two different continuous angles that I've been dealing with in here. One of them is the compass directions for around the circle. And then the other one is if you want to deal with the astrology stuff. The signs of the zodiac, that's their name. So you take a continuous set of angles and you're dividing them into discrete blocks. Yeah. So, but the directions, do you want to do 8 or 16? How fine-grained do you want them? So it's not a fixed number. And then there's 12 zodiac signs. I thought, wait a minute, these are both answering the same question. So I'm going to write a generic function that will take a continuous thing and turn it into chunks and give me names back. Sounds useful, right? Yes. Okay. So really quick thing, the angles around the ecliptic, notice how I said RA and DEC is using the equatorial system. The signs of the zodiac are the ecliptic. And they actually used to get used for regular astronomy, not just astrology. And they were 30 degrees each, and people used to, instead of naming around 360, you'd say like 12 degrees into Taurus or something. And they don't actually line up with the constellations, because constellations are huge, and they're all different sizes. So they just took like the nearest constellation and named a block of angles after them. So there's a pretty picture about what they all are. So here is my really cool generic code. So the principal winds, which is a fancy name for one, so there's the principal winds, compass 16, I got those names off Wikipedia, and the zodiac. So I wrote number 2 symbols, so you tell it what your number is around the continuous cycle, what the cycle size is, so like if it's 360 degrees, or whether it's, well, they're both 360. Anyway, so you tell them that, and then you give it the list of symbols. And it figures out how long the symbol list is. So, and then based on the cycle size, it figures out how big each block should be, then figures out that actually you want the middle of the block, so it shifts everything by half. And then if you're using radians, you've got from 0 to 2 pi, degrees are from 0 to 360, so I wrote helper functions for that. And then if you want to know the sign of the zodiac based on the RA, you give it the longitude and the Unicode symbol. Oh, and then you can have it either output in Unicode symbols or not using my Unicode library. And then I also wrote a function where you could give it a PyEphem body object, and it would figure out based on that body object what numbers it should be putting into the other function. So then I wrote a really, really silly piece of code. So I just told you that the signs of the zodiac don't really line up with the constellations, right? So it's like, wait, so you mean my star sign doesn't actually have anything to do with what stars were there when I was born. It's just some random 30-degree chunk you made up. Well, I don't like my star sign anyway, so I'm going to get a better one. Because in the Western system, I'm Taurus, and in the Eastern system, I'm a boar. Like, can I get something other than horns and 4 feet? So I decided I would write this little piece of code. You give it, like your birthday, and it'll tell you what the sign of the zodiac was. That in astrology, your sun sign is where the sun was, what constellation the sun was in at the moment you were born. So it'll tell you that, and it'll also tell you what constellation it was really in. So it's a really simple piece of code. This is all it takes. And so when I run it on my birthday, I was born on April 27th. I was like, I've got Taurus, I've got a bull, I want something really cool and unique and totally different than something with, 4 hooves. And I got a ram. Okay. Questions? Yes?
Can you go back to that really quick? Because I'm actually really interested in
Yes.
the difference between sidereal
Yeah, I didn't even talk about sidereal.
versus literal zodiac, right? So it's like contemporary astrology.
Yeah.
Every year, right, on March 21st at the Vernal
Mm-hmm.
Aries is going to be the rising sign.
Yes.
Versus, that was 2,000 years ago, where now it's actually 5 years.
Yeah. So actually, if you...
I was thinking if there's like a fancy astrology standard.
Actually, astrology is hilarious because there are several different astrology systems, and I started looking stuff up. Apparently, not only do you have sun signs, you have moon signs, which is where the moon was at your time of birth. And you've noticed you can't just go like on a block of months and look it up in the newspaper because the moon moves really fast. You actually have to know what time you were born. And then there's also the rising sign, which is what sign was at the horizon rises in the east, on the eastern horizon, so it was coming up in the sky as you were born.
But again, that'll be off by about 28 degrees.
You can adjust the epoch too. Yeah, but you can also adjust the epoch. I've done everything here in the default J2000. I didn't reset the epoch. So the problem is when you start getting too far away from today, everything is moving. There's nutation, there's precession, so the way we're moving around the sun changes, the way we're rotating around ourselves changes. So things move a lot. And there are ways to handle this in PyEphem. I'd have to go look at the documentation to figure all of them out, but a big one you can reset is the epoch. Because, yeah, I'm doing everything based on the year 2000 because J2000 is really common right now, but stuff moves. And everything is based on the vernal equinox. Like RA and Dict, we're not in the same place from one year to the other. So where the North Pole's actually pointing might change a little bit, but RA and Dict is based on where everything was at the vernal equinox. What? Okay. Oh, okay. We're about out of time.
Do you have any ideas for the future project that you're going to do with this? Like, or if time was no constraint?
PyPTP, PyGuide. PyPTP is picture transfer protocol.
So you could take a picture and be like, tell me what's in here?
No, that's actually a totally different library. I could use PyEphem to figure out when I want to take pictures and then have Python take the pictures for me, like time lapses and stuff. I can have my computer control my camera. So PyPTP is a good one. If you've got really expensive stuff, there's Python libraries to control your tracking mount for your telescope. There are also Python libraries to do your guiding for you. So if you're fancy enough to have a tracking mount and a separate guider that's sending corrections to the tracking mount, you just import guider and it guides for you. It's pretty awesome. So, yeah.
Two API questions really quick. The
Yes.
first one is this purely implemented in Python, or is there a wrapper on?
There is, yeah, it's wrapped around with the ephemeris C libraries. So that existed before the Python ones, and somebody just decided, I really want to use this in Python.
Gotcha. And then the other question was, how broad is the support for planetary bodies? Like, is there a way to get a list of them in the documentation? What about like asteroids and stuff like that?
I did not talk about asteroids, but there is support for them. I don't know how many of them are built in. You might have to import them yourself. But yes, it does support the funky things that asteroids do. So ask the documentation. It knows more than I do. But yes, you can do that. Okay. All right.